Hello everyone, and I welcome you all to our 4 days live hacking virtual conference VULNCON 2021 organized by NOOBARMY. I hope you all are doing amazing and are perfectly healthy. I am Abhinandan Khurana, your host for this evening, and I shall be accompanied by my worthy co-host Ms. Muskan Bawa. So let's get started with a little introduction. We are an information security open source community which help each other learn cybersecurity and become the better version of ourselves. Give back to the community. This is what we believe. So going to the next number, that is by virtually, we are trying our best to fill the gap between the top-notch speakers from the industry and the people like us who are eager to learn. Up next is the token of appreciation for my team and all the volunteers, authors, speakers who are giving us their valuable time and making this event possible. Moving on, special thanks to our sponsors who are Offensive Security, Hack the Box, Bugcrowd, HackerOne, CyberExplore, DigitalOcean, and yes, VHack for being our sponsors and supporting us.
It's tough being a security professional. Every day, you're fighting a surge in cyber attacks across a dynamic, fast-growing attack surface. But the legacy processes you rely on to manage and audit security haven't changed for decades. They don't fit today's dynamic, digital landscape. They're outdated, obsolete. Bug Bounty takes penetration testing into an exciting new dimension. You invite ethical hackers, or hunters as we call them, to surface vulnerabilities according to strictly defined rules. And if they find a bug, they receive a reward. It's that simple. Organizations of all sizes and industries are rapidly adopting Bug Bounty. So let's take a look at how a Bug Bounty program works. The first step is to define the program rules, which include the scope of what you want to test, the vulnerabilities that qualify for a reward and those that don't, the bounty grid which defines the amount of the reward based on the severity of each bug. The program is then launched in private or public mode. In private mode, only selected hunters are invited. It could be 5, 50, 500 or more. You control the pace. In public mode, the program is launched to the entire Yes We Hack community for the largest possible reach. Once the program has been launched, hunters start testing and submit their findings through the platform. Each report is then validated according to the program rules. If the vulnerability is valid, the hunter is rewarded based on the severity of the bug. Once the bug is fixed, the hunter double-checks that the security exposure is closed. So, are you ready to go? Visit www.yeswehack.com.
The appreciation cannot end without thanking our CTF organizers, Team Dark Army and Mr. Crep. Now, if you want to follow us or if you have any queries, the details are mentioned down in the description box. Also, the cliche line: don't forget to follow us on our social media platforms and do tag us if you share anything related to VULNCON 2021. Coming up next is something we have prepared for our sponsors who have showed us immense support. Hope you will enjoy it, and with this I will be passing the baton to my worthy co-host Miss Muskan Bawa.
So moving to the first talk of the day, we'll have Asim Shrey with us in some time, who will be speaking on getting started with Android pen testing.
Hello everyone, this is Asim. Welcome to my talk on getting started with Android pen testing. Today I'm going to take you through a static analysis of the app. I'll be talking about the process as to how I go through my process by finding secrets, hard-coded credentials, API keys and stuff into the app. I would also talk about some of the tools that I use to automate this process and ease out things. And then I would take you through the code and trying to figure out credentials and places where developers hide their secret credentials, or where you can find secret credentials. There's high probability of finding those. I'll be talking about those as well. So without a further ado, let's get started with this. So you can scan this QR code if you want to get the slides. These are publicly shareable. So as soon as talk starts, you can just follow me along there. A brief intro, or rather bragging about me. So I, myself Asim, I work as a senior information security engineer at Gojek. Apart from that, I have a YouTube channel called Hacking Simplified, where I teach about cybersecurity and stuff, bug bounties, and job scenario in cybersecurity, and a lot of different not so common things in cybersecurity. I talk about those. On Twitter, I go by the handle as Asim Shrey, and I usually tweet about some of the cybersecurity questions or things that are happening in the world around us. Some of the basic concepts, like recently I was talking about this router stuff and network layer things and security around that. So yeah, you can follow me around if you want to get updates on that. Then there's my website, asimshrey.in. In my free time, I work. I also try to secure organizations and government by finding bugs and reporting it to them in a responsible manner. Like this was one of the reports that was published on ET Prime. It was last year when COVID was on Prime in the first wave. So yeah. Then this is a DigiLocker thing. I found a bug in DigiLocker, it's way back in 2017, 2018. And that time using this bug, you could get access to the billions of documents that are there. So yeah, that was one of the things for which the government of India gave me a Hall of Fame kind of recognition on their website. This is a private bug bounty program, so it's not always about securing government, and it's sometimes I also do private bug bounties and earn something from there as well. Let's go through the outline of the talks. First, I'll be talking about what is Android, basic components of it, like the Android apps, then static analysis. I'll be talking about what a manifest.xml is, decompiling and understanding the code, searching for secrets in the code. Then further resources. I'll be also showing you the different tools and how, what are the links for them so that you can easily install them. The first question, the very basic thing that you would want to know is what is Android. And Android is a mobile operating system, as everyone knows. It's available on almost, except iPhones, it's available on all devices, I would say. There are a few other competitions of Android, but those are very minor thing. Even Android is available on mobile OSs as well as televisions. So Wear OS is a variant of Android for those systems. Let's talk about the basic components of an Android app. So Android applications are primarily written or eventually compiled into Java or Kotlin. There's a framework called Flutter, which is based on Dart. Dart is again a language by Google. So, and Flutter is a UI framework on that. So basically, these are the most popular ways people usually write applications these days, either writing directly in Java or Kotlin or Flutter. there's this React Native thing that people use. So people write code in JavaScript that is React Native, and then that get compiled into Android application using the React Native compiler and other kinds of things. That's the whole tool chain that's there. When these applications are distributed, these are a package kind of thing, which is called an APK, which is Android package. So it's a short form for Android package. It's a zip file containing all the assets and bytecode. So if you convert the .apk file to .zip file and then unzip it, you would find all those things there. Android manifest, it basically contains all the basic application information, such as the different permissions that the package requires, what is the name of the package, the version, and what are different activities like pages and external activities. All those things are involved. If you don't understand what an external activity is, it's basically any page on an Android application that is called an activity, and if that page can be invoked by a different application, that's an external activity. Let me just take you through the manifest file, because I think it's getting overwhelming without any demo kind of thing. So here I am on my terminal. So if I show you this, here's this insecure shop.apk. You can get it from here. Let me just unzoom it. Where is this? So there's this repo, github.com/optiv/insecure shop. Here is the downloading. If you click on this, you can download it. This is a document of the different challenges. So insecure shop is a by default vulnerable application, and this is the whole documentation of it. What are different kinds of vulnerabilities? So the first one, that is hard-coded credentials. This is something that we would be trying to look into and trying to figure out this one. The different tools that I would be using is, one is this APK tool. You can get this on this link here, and then there's this, the download link here. They have instruction how you can install it for Linux, Windows, or Mac OS. And this is another tool that I use. This is quite a good UI experience. I'll talk about why I use a mix and match of both. So you would see me doing that. So there's this GUI for this, JADX. JADX is basically text to Java decompiler. So it's that I would be using that. You can get the releases here. If you go to this releases thing, you can get the zip file. It would have a Java or jar file. You can just execute that. For Windows, there's a exe as well. Then the other tool that I'm going to use is GF. So GF is a grep wrapper. Grep is basically a search utility in Starnix machines, or Linux and Mac machine. It's not available for Windows as far as I know. So if you have used grep, you would know that it's very fast to search in through thousands of files. You can easily search through grep very fastly, and you can also do a regex match. So if you feel that the secret pattern is something like ABC dot and then 10 characters, then you can already do those regex matches, regular expression matches, using grep. That's very fast to do, and it's very useful. That's why I use grep. But because these regex patterns which we need to match, those get complicated, that's why I use this wrapper called GF, and it has a lot of patterns already inbuilt into it. So if you go to this, you can see that these are the different patterns. So let's say if you want to figure out AWS keys, you can just see that what is the pattern that's mentioned here. So this is the pattern here. There are a few more patterns that I have added to my GF pattern list. So these are the JSON files that's already there. You can easily go through these repos and understand that how you can install it on your Linux or Mac machine. So let's come back to this. So I was here on my terminal. I have this insecure shop.apk downloaded. Now to use JADX, you can just write this and give this insecure shop.apk. This is all you need to do, and just press enter. It would decompile the app and open it onto JADX GUI. So what the focus here is that we want to go through the files and figure out where the credentials would be. The very first thing that I was talking about here, as you would have seen on the slideshow, we were talking about manifest. So let's first explore the manifest file. Here you can see all the different resources, all the what the different folders are there in the source code that's mentioned here. Then there's this resources folder. If you toggle it, and you would find all different files here. There's this Android manifest.xml. This is also decompiled, and you can see the whole manifest, whatever the permissions and everything. You see, these are the permissions that mentioned already there. So any application that is there, they need to specify what permissions are there that it requires, and that is how once you install the application, they give you that this requires these many permissions. So if they want, let's say, any new permissions, like let's say for example the first time you are using the app, you don't require you don't require, let's say, GPS location. But for a particular functionality you require GPS location. So in some of the applications what they do is they invoke that permission for the for location thing on the fly. Like once you click that particular functionality of the app, they ask you for that permission. So Android, this is how Android gets to know what kind of permissions the app requires initially when it is getting installed. If you read it here, there's this Android Target SDK version, Android Min SDK version. So it is 16 and 29. So basically on what minimum Android version this particular APK would work, and what is the target version of it. If you go here, there's this package name com.insecure shop, and what else? I think that's all. Then there's this application tag. So this is an XML file, so that's why there are tags here. And if you see, there's this IC launcher, there's the icon, how the icon should look. What would be the name of the application once it's running? Is it debuggable? True. Yeah. Allow backup? True. Supports RTL right to left? It's true. Uses clear text traffic? True. So if an application has mentioned uses clear text traffic, then if you are doing a sniffing onto the HTTP traffic, you can easily the Android operating system would allow the application to make a HTTP connection to any other website. Before Android 7, it was not required to explicitly mention this, but after Android 7, this is explicitly required to mention this tag, and also mention this particular thing is explicitly required to mention. Only then that application will be allowed to make a clear text request, like a HTTP request to a HTTP only website. Yeah, that's pretty much it. So let's come back to the slides now. Now we are gonna start with a static analysis of the Android app. We see the decompilation and view. So we have used this JDX GUI for the decompilation and viewing the code. I would also talk about why we need APK tool, and then we will be using GF to scan through thousands of files to find secrets into the app. So the very first thing, let's do some static analysis. So some of the files that where developer usually have secrets, one of them is this manifest file. Usually it's there, like you would find some API keys, Google Maps key or something like that here. The other place that you might find is go to this REST folder. Then there's this sometimes in the XML file also, the XML folder, there are some static raw assets file. Otherwise, let me just open this resources.arsc file. There's this REST folder again. These values, you would see that there are a lot of folders with the same name values, then hyphen, then there are two syllables, there are two characters. So these are basically different translations of this particular app. So let's say if they have strings file, and then the person chooses, instead of English, let's say they choose a Hindi language. So there would be the values hyphen HN or something like that stands for Hindi, and that particular folder and that particular XML file would be used. So if let's say I open this one, there's this strings.xml. So all these strings, this whole thing would be copied into all these folders, but instead of this particular, let's say, so here you can see that for ABC search view description clear, this is in a different language. AF, I don't know if it's African or something. Then there's this GN, it's like the same string has been replicated into different languages. So let's say if the user chooses a different language, it automatically gets the app. They don't need to re-download a new version of the app. Rather, the translation would be used. So that's why this strings.xml would be available in all these folders. So this strings.xml is another file where the hard-coded credentials can be found. So let's go through it from the top. So these look benign, they don't have anything else. If you go to these 5 files, you see that there's AWS Identity Pool ID. There's this pool ID mentioned. This pool ID can be sensitive depending on how the pool is configured. So this is a Cognito AWS Identity Pool. So if you're not aware about this, you can just Google about it. So there's this Cognito offering by AWS, and they have this identity pool concept. I mean, there's a challenge also about this Insecure Shop app. I won't be talking about that particular thing, but this can be a sensitive information if the pool is not properly configured. let's see if there's anything else. Usually they have this Firebase endpoint, and sometimes the firebase.io.com/.json. So basically that Firebase is publicly sometimes that happens. So I usually keep an eye on those kinds of things here. There's Google Map links which can be exploited. So that those are the kinds of things that you might find here. There's nothing here. There's nothing that I could find here. Apart from this, I also look into one of the files. There's this insecure shop. So if you go to the main com.insecure shop folder, there you would find this build config. Sometimes they also add some strings here as well. So have a look onto that also. Then we can go through these particular folders one by one. But I would show you a more efficient way as to how you can search through all these files. And there I would be using grep, or rather a gf, that is a wrapper over it. So let me just show you how that can be done. So let's documents insecure shop app. Now we have used JDX. Now I'm gonna use APK tool to decompile insecure shop.apk. So what this would do is it would decompile the whole app and create a folder with the same name. All these things that you saw here in JDX GUI, all these folders would be as it is created, but instead of because searching here in the JDX GUI is not very it's not very effective, and sometimes it slows down the system. So that's why I decompiled the whole file, because this whole thing is in memory. There is no actual file created, so it uses a lot of RAM. So to avoid that and to be faster on that, I just decompile it using APK tool. So here you can see this folder, and let me just go to this folder. If you can see, there's this Android manifest.xml, there's Kotlin, there's original, there's rest, there's Smalley. So let's say if I want to do what's there in original, there's nothing a lot. I would go to Smalley. Smalley, you can see Android X, com folder, Kotlin X, net, org. If you see, there's a similar structure here. Android X, com, Kotlin X, net, org folder. So inside com, I would go into cd, Smalley, com. Now let's look. So here's this insecure shop, there's BumpTech, there's Google. And if you see here, these are the same folders that's there. Let me go to this insecure shop. Now you might ask, Casey, why are we going into this particular folder? Why not we just doing a grep in the whole thing? So we want to find secrets in this particular app. That's why we are going through this particular folder, not the whole app. Because if we go through the whole app, we would find some unnecessary data in a different folder that might not be relevant to this. So that's why we are doing a search onto this. So let's say I want to do grep -i secret dot ir. So R is a recursive search, so it would go inside all these folders. If I do this, you can see that these Smalley files. Smalley files are basically this. What do you say? If I show you here, let's say go to this about us activity. So activities are basically a single page on the Android app is called an activity. So this JDX GUI has decompiled it for us so that it can be readable by human, and that's why we are able to see this Java code. Whereas actually if we do, there's this Smalley code out there which is in between Java and machine code. This is also human readable. APK tool, instead of decompiling to Java code, it decompiles to Smalley code. So you would find that it's similar, like about us activity.smalley. Here it is about us activity.java. So it's the same thing. So I did grep for secrets, but how many of these, this would match a very basic thing, right? So I would want to match a lot of patterns. So I would use gf, and then these are the different patterns that I have on my machine already. I've already told you where you can install this. It's from here. GF, you can install GF from here. You would have some of the default patterns from this. Some of the patterns you would already have once you install GF. For more patterns, you can install it from here. These JSON files are what you need to copy into the GF folder. You would get the instructions here. It's very easy to set this up. That's not a hard thing. So let's say I want to check for AWS keys in the whole thing. So there are no AWS keys. Let's say I want to check for Firebase thing into this. There's no file. Let's say I want to check for URLs. What the HTTP or HTTPS queries, because sometimes you might find some sensitive endpoints which are written into that. So that is something I would want to look for. So let's say I do this. So you see that these are all URLs that I find into this particular application. Let's say S3 buckets or something I would want to check for S3 buckets. So it has patterns for all these things. It checked the whole application code for any S3 bucket patterns. So I didn't find anything. Let's say I want to check for all the strings that's there in the application. Now this is a big one because it would give you any string, anything that is inside double quotes, it would just print it out, and that's why it would be a huge one. Let's see how many things. So you can easily see that there's a lot of this here, and if you see there's this password or something like that, that's coming up here. If I go to this, there's this insecure shop provider.kt. KT is Kotlin file. What else? Let's just go through this once. So if you want, you can just like push it out into, like, you see that there's this view and then this is twice, inflator is twice. So what you can do is, I prefer doing this, having this piped into a file called, let's say, all you can do is sort -u. So it would give a unique sorting of these, so you won't have like those findings twice. So value and values, you won't have it twice. It's like alphabetically sorted, and you would have like how many things? Let's say how many. You only have 533 strings, so that's easy to find. If you would have done just this, there were 1513. So like there were thousands of strings that were repeated, right? So WCLS command to just like do word count kind of thing. -L is for new line. So now 533 is easily, like, we can view things and we can figure out. So let's say just go through it once. So you see that these URLs are again those things that we found earlier as well. And what else? Nothing looks like something sensitive here. If I remember correctly, there needs to be a secret or something like that. LCOM are basically files. This is something you can ignore. So this is something that looks like a username or password kind of thing. So this is something I would like to explore where this is. So what I will do is so I did grep -ir, and this particular string, it was found in util.smally inside utils folder. So instead of going to smally, I would just check it into this util and utils folder. So this is where you find. So this is insecure shop and shop user. And if you go through the code, that is something I would want you to check through. So let's say there's this login activity, and there's inside the login activity there's this onCreate function. So onCreate is a lifecycle event. So this is the first thing that gets executed. There's this onLogin thing. So that kinds of is understandable that okay, it's onLogin thing. So here it's trying to get the value of a username and password, if you see. And then util.verify username password. If you press Ctrl and click, it would go to this application. Check parameter is not null. First it's checking whether the username password is not null. Then get user credentials. So this is the get user creds, and it's checking these things like username and password from this. So basically this is the username and password for the login activity. So you figured it out. So there were two methods to go through this. One was using gf, and then like this was the command here. This was the command, and once we did this, we found okay, there was one string that was suspicious to us. So what we did was we just searched for that particular string. We found that this was the file. Then we went to JDX-GUI to look for that particular file inside the utils folder. There's this utils one, and there we found that okay, this is there. We reversed, or we could have directly gone to the login activity. So this was the first way. The second way was going through the login activity, the proper code thing. So if you open the application on your mobile phone, you would see this login activity being popped up. And we read through the code. We found that there's this onLogin function. Then there's this verify username password function. Then we went through this, and here we found that okay, this is being called, like get user credentials are being called, and then this is the username password that's being expected from the user. So that's how I figured out another like secret hard-coded credentials into the application. Let's come back to this. Some of the resources, you can easily click on this and get this. Yeah, that's pretty much it. If you want to further connect with me, DM me or follow me on Twitter, or anything you want to ask, you can just scan this and you would get all the links. Hopefully this was an informative session and you learned something new. If you have any questions, make sure to connect. Okay, thank you. Have a nice day.
Thank you so much, sir. Hope you all have learned a lot from him. Now moving on to our next speaker, we have Yusuf Somida with us on board, who will talk on hunting for uncommon bugs in client-side applications. Over to you, sir.
Hello everyone. Today we're gonna talk about the profitable way to find vulnerabilities in client-side web applications, presented by me, Yusuf Samoda, cybersecurity researcher and consultant. First of all, table of content. As you can see below in front of you, about me, bug bounty hunting, requirement to enter the bug bounty hunting field, and lastly, vulnerabilities in web application in the client side. About me, I started the field of information security 5 years ago. After learning and applying my experience, I focused on trying to help emerging and global companies to patch security holes in web and mobile applications through bug bounty programs mainly, and also doing security consulting for private companies. I found more than 120 security vulnerabilities, thanks to God, in companies such as Facebook, Vimeo, Tesla, and Quora. Most of these vulnerabilities were in Facebook, and most of them were critical, which made me ranked first in the Facebook bug bounty or white hat program in the last 3 years. Here you can see some of my most critical vulnerabilities. As an example, I found a security vulnerability that allowed me to show the content of error messages and internal exception due to a defect in deleting some Facebook objects. The content of the exception was information about each object, such as Facebook user or company infrastructure. I got $81,000 for this bug. Also, several loopholes enabled me to read internal files from internal CDNs. I got 45,000 for this one. Also a bag that allowed me to steal personal information of any user, such as private photos and messages. This one was due to the ability to create access to API access token for any user, Facebook user. Also, several loopholes allowed me to hack Facebook account by deceiving the user to visit a specific link that exploits a loophole against him or a bug against him. Today we're gonna talk about this type of bugs, mainly client-side web applications bugs, and yeah. This is the annual ranking of the Facebook Bug Bounty program. This photo of me and my team members at a global competition organized by HackerOne. How and the requirement to enter the field. It is rumored that this field is for everyone and you only need a limited knowledge of some concepts and attacks to enter it. And this is a common mistake and it should be noted. The bug bounty field is not much different than the field of application security engineering or penetration testing. it is true that in this field you are not under management or of, for example, of higher authority, which may blame you when making a mistake, for example. But this does not mean that you are completely free to enter the field without prior knowledge or study in order to succeed first and also to get good like a good reputation that enables you to work in international companies later. We'll try to give some requirements to before entering the field, and which I personally see as necessary. First of all, programming, like because vulnerabilities are errors or malfunctions in uh, in the application developed and directed to a specific category of customers. You must understand the software codes and functions in them to be able to detect places where a feature can be abused. And this is actually the bug. Although most companies do not publish the source code of their applications, if a security researcher is familiar with programming and the widespread methods to program a feature or a function, he can predict the possibility of some errors and then directly search for them. The best example of the importance of understanding some programming languages and code is the type of bugs or vulnerabilities that I will present today, which depend a lot on understanding the programming language, JavaScript, and the HTML markup language. Of course, here, if you're interested, for example, in web applications security, you may try to learn about PHP or learn PHP or JavaScript, or even only JavaScript and its applications in client side and the server side, like Node.js. If you're interested in mobile applications security, you can learn about Java or Swift for Android or iOS development. Uh, Learning approach. The approach to learning how to find vulnerabilities is, as we mentioned, first knowing about programming and various functions, protocols, and the internal technology used. Here, for example, databases or LDAP, or I'm not sure what else. SOAP, for example, used and how they work with each other internally, and then studying what types of attacks that could be launched against these, and knowing what are the possible vulnerabilities that could occur before knowing how to find or exploit them. Among the most important sources of knowledge, to my belief, are like to learn, first of all, to learn attacks and attacks techniques. There are books, write-ups, and security white papers. While reading these resources, you must apply what you have learned and continuously and immediately practice in order to be able to further understand and study other cases of how a vulnerability exists or how to exploit it. Also, the best ways to train, to my opinion, is participating in CTFs, doing labs like Portswigger labs, and also hunting in VDPs programs, vulnerability disclosure programs. Here are some resources and references. Importing blogs and websites, also some books that I'd recommend to read, very interesting ones. Here are some security experts on Twitter, also I'd recommend you to follow them. Also practicing here, you can find like CTFs, HackerOne, VDPs programs, also OS vulnerable web application. As one of the ways of learning is to try to program applications that are intended to have a particular bug, and then try to exploit the bug yourself. Perhaps this will not teach you how to find the bug, but will help you improve your exploitation skills. Also, some books, guides from Aws on how to find and avoid security bugs. Very good resources. Some links to report bugs in different websites like Facebook, Google, PayPal. Vulnerabilities in client-side web applications. Web applications on the client side are a set of codes that are written in JavaScript, which are received by the browser in the form of a text, and then we can say compiled and run for performance here. This enables us to do complex things on web pages, like every time a web page does more than just sit back and show you static information, like how it was back in the 90s, I think. But these programs allow developers to update content in time, show interactive maps, for example 3D animations. With these features, several security challenges arise to ensure the safety of information and customers. So far, I have tried to explain most of the terms and concepts that we pass on, but understanding the following attacks requires some simple knowledge, such as the content of messages in the HTTP protocol and its format, also knowledge of JavaScript and the two markup languages, HTML and CSS, also like parse names of the link or URL. Here are some important terms to understand the attacks. The DOM, it's found in JavaScript, which is the model of representing the page as an object, or document object model as it's called. And it contains all the component of the page in the form of objects as well, and it is considered one of the basic methods for building interactive websites. Source, any Java, this source and sinks and are like terms we use in exploitations of like Css attacks or prototype pollution attacks. So the source is any JavaScript feature or function that accepts data from the user. Simple definition here. A sink, any feature or function in JavaScript that consumes the data from the source in an unsafe manner. DevTools, a set of tools in the browser that enables you to analyze and modify the content of the page and watch the process of running JavaScript codes. URL query, it's the part of the link between those two, like exclamation mark and the hash. The URL fragment has the part of the link after the first hash. What's next? So the first attack here is prototype pollution. Definition: JavaScript depends on the prototype. When new objects are created, they will carry properties and methods of the object's prototype or the inheritor object prototype, which contains basic functions such as toString, constructor, and has own property. Object-based inheritance gives JavaScript the flexibility and efficiency that web programmers have come to love. but also makes it vulnerable to manipulation, or in this case, prototype pollution. There are several ways to discover the prototype of an object. For example, using this method, get property prototype of. Here, as the example here, here we have returned the prototype of almost every object in JavaScript, which is object with a capital O. When accessing a property of an object via x.name, it actually does the following. First, the JavaScript engine searches for the name property of an object of the object X. If present, it is returned. Otherwise, the prototype of the object X is selected, and its properties are searched to find X. The inheritor in turn has a prototype, also its parent inheritor as well, and so on. This sequence of prototypes from object to null is called a prototype chain. In the case of object X, the chain is short, like in the example here. X is an object like we created X before, like here. X.proto, for example, here there is a typo. X.proto would give us null, since the chain is would only contain one prototype of the parent, which is object, the main object. Malicious actors can make application level changes to all objects, like by modifying a single object, hence the name prototype pollution. In this case, the attacker doesn't even need to modify the object directly. They can access it through the proto property of any object in JavaScript. Once a change is made to the main object, it applies to all objects in the running application, including those created after the pollution. Here another example. We have an object called person. We first console.log the toString, the result of toString function. Then we access the prototype of person and override toString function to do an alert contain change. We later recall toString function of person, and we note that now we have an alert containing contain change instead of as before object string is shown. Here we define object administrator contains two properties, name and is admin set to true. Normal user name me is admin false. Here is more of a server side example where each user has a property called is admin, but it can happen in client-side applications, I think. Third, user, an object not identified user, empty object. We first console.log normal user is admin, which should be false. Also, we try user is admin, which is undefined at this point. Also, we now access like we try to access the main object by accessing the prototype of window. We try to reach the object, the prototype of object, but from the window object, and add is admin, set it to true. This should like replace any in the any object where is admin is not set, it would replace to true or be set to true to be more accurate. Later we try console.log user is admin. This was undefined, but now since if is admin is not found in the user object, it would JavaScript would look in the prototype, and in that case it would find is admin and set to true. Also normal user is admin, it was false since it's present, it's a property of the object normal user. It would return that property value and not the one from main object. Vulnerabilities and attacks. We can use prototype pollution of an object to launch many attacks. For example, to achieve DOM cross-site scripting, and here it is possible because the client-side code and not due to lack of filtering when returning data from the server. After manipulating or adding properties of some objects, we can extract data for the user or session. What do we need to attack? First, we must find the code with the weakness that allows us to pollute the prototype. Initially, we should find the source, which is any function that saves data coming from us. Then we follow how the data was used, and is there really a code with a bug that would allow prototype pollution. Fortunately, there is a pattern in the codes to find this vulnerability, which makes it easier for us to search. After polluting the prototype, is there any application logic or function that could cause malicious JavaScript to run or to be run or to extract data? This process is called finding a vulnerable script gadget. Common sources that we control. We have window.location.search, the query part of the current URL, location.hash, the fragment or hash part of the current URL, cross-window messages via sent from the attacker page via post message. Of course, the targeted page should have an event listener listening for cross-window messages and using these messages safely. Document.referee, the previous link that redirected or who referred us to the targeted page. Also form inputs. The inputs on the page, but it's very rare to happen. Some patterns in codes like vulnerable code. Common functionality in the application that might cause prototype pollution is the merging of properties of two or more objects. This process is called merge. As you may notice here, this code is a recursive function that would copy properties of object source to target. Here, an example to using of polluted objects. Actually, this code present a vulnerable source and sink. The vulnerable source is a get tracking attributes functions. For example, here is an example of code that takes data from the link, the current URL, and converts all this data as a key and value pair onto an object. Here is the object tracking data. And then adds or combines these properties with the properties of an element in the page document. Not exactly an element, but any object here called element object passed as an attribute, as an argument to get tracking attributes. But in this application, a document element was passed. This leads to the ability to add and run JavaScript codes after adding inner HTML contained in the current URL, of course. We don't actually need here to pollute the prototype object, but like we can use this and then look for script gadget elsewhere in case we didn't have the possibility to with the element with the merging with an element object. Ways to find this vulnerability. First of all, attempting to review the source code and search for potential sources using keywords such as, like we mentioned this before, location.ref, location.hash, location.search, document referee, and verify if they are used in a merge or other similar operations. To be honest, this is the most difficult method. The second method is programming or using tools that inject the important places in the links with the payloads, and then verify the success of the pollution or contamination. We have some tools here like ppscan and Selenium Boat. Second, we can check if the polluted object has been used by manual scanning after searching for keywords like source doc, inner HTML, iframe, create element, or by using tools such as pollute.js or untrusted types. Here, an example of vulnerability found of this type prototype pollution in the HackerOne platform. Full article could be found here, of course, the URL for this report. HackerOne, actually the subdomains www use JavaScript to display videos from platform Wistia, called Wistia. Some lines of the code used. We can notice that location.ref and document.referee were read and their content was placed in the variables u and t. This is a potential source, both of them. To make sure that we have here the possibility of prototype pollution, we put proto test equals vol in the link in the current URL, and then check that the test element has been added to the object prototype. If not, we can try with the proto test, for example, and so on. The researcher found test, which means that the prototype of object has been polluted after polluting object. We should now find a script gadget, any function that uses the polluted object in a dangerous process. Her researcher find a function named element from object, which creates an element in the page like a new tag and adds attributes from the object passed as argument to function. Of course, to the function lm.fromObject. Since we have polluted the prototype, for example, with test, any object will now load the test element, and thus the object passed to element from object. Here the researcher, of course, has added HTML and JavaScript code in inner HTML instead of test via the current URL, which means that any element or tag on the page will have the inner HTML. Actually have to be accurate, any element object in the page will have the inner HTML from the attacker. To those who don't know, inner HTML is the literal writing of the element, and that will be placed in the page. Here, the researcher was able to get the DOM XSS. Here, the code to use element from object. As you can see, this object with attribute with properties like ID, class, style, tab, and text was passed to that function. Of course, here after the prototype was polluted, this object would also contain inner HTML, and thus would lead to DOM XSS. Here is the link to exploit the bug simplified. As you can see, it accessed inner HTML, proto inner HTML, and a simple script to execute alert one. I think in the original report, CSP bypass was needed. This shouldn't work. Next, we have another vulnerability, DOM XSS. DOM XSS is type of XSS attacks when the payload is executed as a result of modifying the DOM environment in the victim's browser by abusing the application on the client side, so that the client side code runs in an unpredictable manner. That is, the page itself, like the response from the HTTP request, does not change, but the client-side code on the page is executed differently due to the malicious modifications that occurred in the DOM environment. We check that the information coming from the source is going to danger. Here we can, like, the way to find this vulnerability would be to check that the information coming from the source is going to dangerous places or functions that led to the possibility of attack. These functions are called, as we mentioned before, called sinks. Here are some examples of sinks functions. We have document write, document domain, location ref, element inner HTML. Also some examples of sources, vulnerable sources, of common sources. Example one, the following code, as you may notice, reads the content of location search via the URL search params function and lets you create an object from the content. This is the source part, and securely passes content to name elem.inner.html, which changes the content of the element in the document. Here the sync part, of course, here we can achieve DOM XSS. Example two, the following code rise to the page or document without an escape action. Escape, or we here mean to remove or encode HTML characters. And the content is from a source controlled, of course, by the attacker, which is location.ref, which is the current URL, or in other words, the current URL of the page. Third, example 3, the following code reads content of document referee and creates an object from it, source part here. It then checks for a property in the object called initRedWays, which is a field in the query part of the link. And if found, moves the page via location.ref to the properties value without making sure if the link starts with HTTP or HTTPS. Here the sync part, which allow us to use JavaScript to enforce the redirect to to a JavaScript link and the shift DOM XSS. Tools that can be used to facilitate the search process. DOM XSS here or DOM snitch. Also important references. Next type of attacks, website attacks. Website is a protocol in the web similar to HTTP and differs in the way the communication between the server and the client or browser happens, and its speed. The main difference here is the speed. Website is near real-time communication protocol. The switch to using this protocol is done after presenting the page of website via the HTTP protocol, and then using an API in JavaScript that enables you to establish a website connection. Attacks, the server checks the origin of the request via the origin header, of course sending the HTTP request, and compares if the site that sent the connection request is whitelisted. Of course, the check here is done server side. Course security feature does not apply with WebSockets, unfortunately, which means that cookies are sent whatever happens in the initial request, and the majority of server-side applications would use received cookies to identify the current user and also to resume the HTTP session in WebSocket. In summary, here is the application of the server fields to verify the origin and later use the cookies sent to identify the user and return his data in a message. This means that we can, from our website, talk to the server and steal information about other site user, other website user. Example here. Here is an example of a code that opens a website communication channel with a website that does not check the source of the request of the origin, as we mentioned before. Cookies are also sent here, which means that the users of the original website, when they try the page, when they visit this page hosted in the attacker website, with the following code will be vulnerable. They'll be vulnerable to be attacked. We send a message informing the site to return user data as we here get profile, and we wait for the response with the data here by setting up the listener on message, the on message event listener. Of course, here the message sent can be to change your password, but it's not very common, to be honest. Or, for example, to return an access token used to use the website API. Here, a tool that can help you debug the website communication. You can specify a target to connect to and check if it accepts this origin. You can play with this. Here's an example of vulnerability I found in Facebook of this type. This vulnerability allowed me to take over Facebook accounts of users in my local network only, and also phone users or mobile users who installed malicious application I own. The vulnerability simply appears because the Facebook subdomain, which was using WebSocket instead of HTTP for communication, was allowing local IP addresses to be legitimate origin to establish a connection via WebSocket. So here, if the request to establish WebSocket connection was sent with the origin header from a page that has a local IP address, it would accept this request and establish the connection. Of course, as we mentioned before previously, the browser sends cookies, which allows the server to use them to identify the user and send him his personal information. This happened too of course, with Facebook. The following code is the exploitation code, which should be hosted on a page with a local IP address like this one. We cannot target any user, unfortunately, with this bug because the local IP is only available to users of the same network. So this vulnerability targets Facebook users in the local network, like your home, workplace, or restaurant, or university, for example. The vulnerability was patched by ignoring cookies when the request is from a website with a local IP. So cookies won't be read and it would ask you to log in again. They did not reject the local IPs instead of the other solutions because they actually used this internally for debugging. I got $12,500 bounty for this bug. Also, you can find the full I type here. Cross-window messaging attacks. A definition, cross-window communication allows applications running on different domains to communicate in a secure manner before entering messages via Windows or before introducing this API. Communication from different origins and domains between iframes, tabs, and Windows was restricted by the same origin policy and enforced by the browser. The developers used many hacks in order to accomplish this task, and most of them were basically insecure. For example, trying to communicate using the window.name, using Windows name. The messaging API introduced a post message method through which regular text messages or more complicated messages can be sent across different domains. It consists of two parts: the message and target domain. Of course, here there are other things like transferable objects, but we won't talk about these today. To receive messages, the receiving website needs to add a new event handler or event listener, sorry, and the next event has the following. Sorry, there is some confusion here. So the event listener should be listening for messages or cross-window messages, and the function handling the received message would receive like data, like the content of the incoming message, origin of the sender, which is the origin, also the source, which is the window that sent us the message. Here is a simple code to send a message, cross window message. Here is the region that the message is allowed to reach. Message is the message contained. Opener is the window that will receive the message. Here the opener represents the window that opened the current window. If esam.com is not open in the opener window, then post message will not send the message. Okay. Here is an example code to receive a message. Here we have the handler used by add event listener for messages. The handler would check the origin of the message sender. Here, event origin should be Google, www.google.com, and also the event source should be the window opened, which is the window that we previously opened. Add event listener, we said we already talked about this. Okay, I hope you understand this code. It's very simple. Attacks, the previous codes are examples of the correct use of this feature, as we check where a message should be sent, and also in the other window we check the source of the message that we received, and also the window or the source it sent. These checks are important, and if they are missing, or this means that we have a vulnerability that can be exploited to launch any attack, basically. Here an example of code that never checks the source of a message. It doesn't check neither the source or the origin. It would set the inner HTML or set the row content of the element, the element to anything basically received in the message, to be precise the document property of data which is the message received. Of course, that the message could be string, could also be an object, any clonable object, basically. Here, this code is an example of code that checks the source of the message, but in a wrong way. Here there is a bug in the regex because it misses an escape dot. Like before, here we have an escape dot before com, but we don't have one before Google. So here it was intended to match google.com, any subdomain of google.com. However, because of the missing escape dot, an attacker can use any domain or register a domain like anything here, google.com, and messages will be accepted from this domain. And of course, here we can achieve XSS, DOM XSS. Here, a vulnerable code that would basically send a message containing the information, personal information of the user to the opener window without verifying the target origin, or if we want to send this message to specific origins only. Also, it's not recommended to use the star at any cost, of course, because it's not secure. An important tool that will show you if there are event listeners for cross-window messages in the current page. Post message tracker, great tool by the great France Rosa. Example here of a bug that I found in Facebook exploits the same bug that we talked about. The following code was found on Facebook page. It would create an event listener for cross-window messages and would wait for a message whose sender has a domain or origin owned by Facebook, like for example www.facebook.com or portal.facebook.com. If a message arrives from a valid domain, as we mentioned, it creates a form and puts the action attribute of this form from the message received Here they checked the source of the message correctly, but failed to filter the message content or how to use this message content. Why is that? Because here, if we put the action value to a JavaScript link, we can run JavaScript codes. Of course, there are no CSP rules that made us unable to do that. Of course, we cannot do that so far because messages are only accepted from Facebook domains. In order to be able to exploit the bug on the previous page, I must find another Facebook page that sends a message whose content is controlled by the attacker or by us. A page with this specification has been discovered that used the query from the link on the server side to return a HTML page with this code. For example, if we specify test equal test from us, like here the part here in red, we notice that the response would contain JavaScript code with test set in post message and sending that message to opener. We can now send messages from a facebook.com domain, and we also control the content of the message, so they will be accepted on the previously mentioned page. Of course, before that, we should establish a relationship between the two windows or that host the two pages, page proxy and redirect.php. This could be established using this piece of code. It's very simple. We first open, this is an attacker page. When the victim clicks on a button, it would open payments redirect.php. Then instantly it would redirect the current page to page proxy. Of course, this page, this vulnerability was found before corp was was used in Facebook. Here is if we put all these details together, we can get a DOM XSS vulnerability in proxy page after sending a message containing a JavaScript URL, which will be put, as we mentioned, in the action attribute, and then the form will be, and then the form would be automatically submitted. The following code contains a way to chain all weaknesses found. Here, as you can see, we would set a tab URL to JavaScript alert one, a simple poke, of course. Facebook fixed all vulnerabilities by making action attribute only accept HTTPS links or URLs, and also not using post message method in redirect.php anymore. I got $25,000 for this bag. Link to the full write-up here would be found here. Injection attacks. Ejection attacks differs on the client side from the server side. On the client side, the places and types of injections are limited. We have the ability to inject CSS, JavaScript, or HTML. In all of these cases, the injection does not necessarily lead to adding or running JavaScript code, or in other words, XSS. But the injection could only help us, for example, to extract valuable information as tokens or CSRF tokens or user information. Types of injections, as mentioned earlier, mentioned earlier, any injection point in a HTML page, JavaScript code, and even in CSS can lead to potential abuse. First example, HTML injection. The malicious user is able to control an entry point and is able to enter random HTML code onto a web page. This vulnerability can have many consequences, such as allowing an attacker to modify the page content and use it to launch phishing attacks. This is the simplest form of attacks. We should mention that HTML injection may lead to XSS, but not always. And thus, this name given instead. I mean, the name HTML injection was given instead of XSS or cross-site scripting. Possible attacks will be demonstrated in case running JavaScript code was not possible. Example code here. Here, an external script has been added that contains a function called DOM purify, as you can notice in where is this? The red part here, which is one of the most famous and safest ways to sanitize or clean codes from JavaScript, for example, and enable HTML only. Of course, it depends on arguments passed to this function. We have the source here, and it's the query part of the URL, source of, as we talked before, the source and things. The source here is the yellow part, the tracking object with which reads the location.search and assigns a key value pair to that object from the current URL. What was here? We have also document. This is a potential sync document via inner HTML. We sanitize what we had extracted from the URL and appended to inner HTML of an element with ID tracker. Here we can't get DOM XSS, unfortunately, even though we control what is written to the page via inner HTML, simply due to DOM purify. So we have partial HTML injection, and we'll try to exploit it. Example code that can be injected onto the page. Here's a simple attack of phishing attack. We'll focus on the second attack here. This attack is complex and even requires a separate like chapter, but for the lack of time, we will explain it here in a quick way, but summarize its concept. Here we'll use an attack famously known as DOM clobbering. It is an attack that allows us to add variables to the window object, global variables, which is the object that represents the window, and in it we find the global variables that we created. This is possible because the elements or tags added to the page or document have some attributes like name or ID, and the content of these attributes becomes a variable in the window for easy recall or use of the tag. As an example here, we create an A tag with ID A tag 1. Later, if we use console.log window.a tag 1, we should have it should return a reference to that tag. Here also we notice that there are some window.config has its content either window itself, window.config, because we have or or a new created object. Here we have this style of coding because to avoid that window.config was defined before. So either it's window.config, or we create a new object with these with details below, like version 1.2 test set to false and test path set to that. Since we come from the previous example, we can like put config instead of a tag 1. Like the previous example, we set a tag 1 the name, the ID of an a tag. Now we can replace a tag 1 name with config. This means that we have window.config now defined, and because of the or here, the first option is chosen, which is the one that would be the window.config will now represent the element, the a element that we create that has the ID set to config. Of course, here this is possible because the definition of window.config is after the HTML injection part above in yellow. Also, since the tag does not have any JavaScript code, it will not be deleted with don't purify to sanitize. Here we're talking about the if we inject an a tag with ID set to config to manipulate, to try to manipulate the window.config object. Example code that can change the content of a config. Here we have an a tag with ID set to config and ref anything. We can put content to config.test by placing content for the first attribute ID, the name. As here, ID was set to config, name was set to test. We can also put content in config.test path by placing the content of the ID itself, config, and changing the name to test path. As we can notice here, so ID equals config, name equals test path, and ref equals ysam sc.js. This is like the URL for the malicious script to be included in the page. Of course, this requires time to understand, especially DOM clobbering, which I'll try to do that. We can combine the two, although the two examples previously mentioned, although the ID must be distinct in the page, but this is oddly possible. So if we set ID equal config and in an a tag, then inside that a tag we also specify ID set to config. It would somehow create a confusion and I'm not sure what it is called, document, like two documents, two reference to a document element. Of course, by the way, this is a technique I think found by Turjank. I'm only here trying to explain it to you. We should mention that here config.testpath.ref has content or value and which is ysam sc.js, Let's go back to the first code and see what it does with config.test and config.testPath. So this piece of code in the top, we were able to both set test and also test path to this value. If we check here the code in the highlighted in red, we can see that test path.ref was set to test module. Then we create a script element, then set the source of the script element to test module, and then append that element to the body. Of course, here we have test config.test, and we also control config.test path, which means we can now inject code, inject JavaScript code by including a malicious script, external script linked to a script. Also here we have an example of a partial HTML injection across domain attack to steal data from the page in situations where an XSS attack is not possible, in the event that the application filters contained from methods that enable JavaScript to run, not like don't purify because it avoids this attack, or because we have rules in our CSP that prevent it. Here we have in the head of the page message listener, which would replace, would say the inner HTML or the HTML content of the header heritage with ID header to the message content. Of course, as we mentioned, we can't have XSS because it's blocked. JavaScript is blocked via CSP. Here we have a form that contains the hidden input and the CSRF token. We try to steal that. We know that we can see that the action was set to index.php and not /index.php. And this is a common and serious error. Of course, if you have a partial HTML injection, there is a tag that enables us to change the URL used in the document in the absence of the domain part of any URL. Similarly, in this case, in the action attribute case, or the URL set there, if the tag base, we can use the tag base. Of course, if it's not used, it would set the origin or domain of that URL to the current one. So, example of the attack code here, we send. We open the window containing the previously shown code, verbal code. Then, after opening that window, we instantly start post message to use post message or sending cross window messages to that window, and setting base ref to attack website. What would happen here that we can go back. The form action is automatically submitted after 10 seconds. So now it would submit this form to attacker website /index.php and with including the CSRF token. And this way we can steal the CSRF token of that page, then launch other attacks like to change password or add email and then take over the account. Okay, we have JavaScript injection. We'll pass that. It's basically XSS. CSS injection. Most people think that being able to run JavaScript code is the only way to exploit a bug. In that case, an injection bug. This attack, in the event that CSS styles can be added via a link or directly to the page contained, enables us to steal information from the page without need to add HTML or JavaScript. There are different types of CSS attacks, but we try to only show a few examples. Here's the code as you may see. The vulnerable code here. We have a source that would read the current URL. Then it would insert a style sheet or a link to a style sheet or a CSS file. So here we can inject any CSS style in the current page. What we can do, we can add the following CSS code, which would basically do this. If the input with name password has a value that starts with A, we would require the background color set to this URL. This URL would log the current try A with logger.php A. If this is correct, of course. If not, it would try every letter, and after that we can try the next one and the next one until we find the full password. This is just an example of an attack. Question, sorry, wasn't able to show more attacks due to the limit of times. I can accept questions now.
Well, that was amazing. Now let's heat up the level because it's time for our Dokshad Mishra will be speaking on the art of anti-debugging.
Hello everyone, Dokshad Mishra this side, and today in this session we will be talking about art of anti-debugging, as in we will talk about how anti-debugging is implemented, various ways to do it, and various uses where it can be used for something. So this is my brief introduction. Currently I am working as a malware security researcher in Optics, focusing on Linux and container side of things. In malware I focus on offensive as well as defensive side, as in I try to figure out new attack vectors as well as try to figure out how to detect and possibly prevent those attack vectors. Apart from that, I am a Linux and open source enthusiast. I love presenting in various security related meetups and conferences across the globe, and you can get in touch with me on the LinkedIn with this username. So this is today's agenda. We will start from basics of anti-debugging and their uses. Then we will cover some techniques in detail to detect debuggers, to detect certain artifacts which are created when a process is trying to debug another process. And then we will see some demonstrations, some source codes of their actual implementation. So at very basic level, anti-debugging is just a bunch of techniques which are used to detect and sometimes prevent debuggers and related analysis tools. For example, there are tracing utilities like ltrace, strace, and then there are sandboxes like Cuckoo which rely on such tracing tools. So if we engage in anti-debugging, many times we are also able to detect and possibly prevent a large chunk of tools by same set of techniques. And most common uses apart from malware for this anti-debugging has always been anti-piracy things, mostly to prevent someone from blatantly copying your software without paying you. Then we move to detecting debuggers, and then there are many techniques. So the easiest one to implement is something called timing analysis. So the basic idea is that if a program is running outside debugger, it will run fast, and if someone is trying to debug it, someone is trying to inspect what exactly is going on, it will take time. So if we measure time between runs and then we compare it with some known threshold, then maybe we can say that okay, if it takes something more than this amount of time, then probably someone is trying to analyze what we are doing. But then this is not really a very reliable method, because time taken to run the same code differs on same machine from run to run, and if we are comparing across different types of hardware with different configuration, then it changes from one machine to another machine rather drastically. And if we are moving to certain slow hardware, for example some very old CPU or rather constrained machine, then timing analysis basically fails to work properly. So this is not really a reliable method. Now for implementation, we can simply take timestamp before doing our critical work, where we want to monitor whether we are being analyzed or not, and then we can take the timestamp after doing it, and then we simply take the difference, and then we compare with some known value, and this known value is generally taken by some trial and error or some sort of repeated measurement, and then taking a safe boundary. So this way we can say that okay, probably someone is trying to analyze our code. So for demo, this particular technique is really easy to see how to implement it. For example, we can look at this particular code. So this is where we are doing our stuff. So this is a tight loop where we are going to measure this, and what we are doing here, that we are taking timestamp before this inner loop, then we are doing something in repeated loops until we detect that this duration has gone with more than with some known duration. Then we say that okay, maybe someone is trying to analyze our process under some sort of debugger. Now if we want to see how exactly it works, we can probably try setting a breakpoint somewhere inside this inner for loop, we can then try to see whatever is going on there, and then we continue this program, and then this will basically fail. So that looks something really simple. We can run this tool, and this will just simply go on and on and on. So for debugging, what we can do, that we can do this. We can attach to this process, we can check at entry point, we can come here, we start here, and then we can probably check the source code where to stop exactly. Now what we can do, we can probably set a breakpoint at line number 24, and then we continue. Then maybe we can continue and continue bunch of times, and we simply remove all the breakpoints and continue. And now it says that debugging attempt has been detected, and it has taken this much time instead of whatever threshold we have set in our code, and this process has terminated. So this is one way to detect this. Now another method is that is also commonly seen in various malware samples is that they try to go through the list of all the processes which are running, or maybe they run some sort of heuristic to figure out if there is a debugger that is attaching to their process or has already attached to their process as a debugger, and then they try to match it with some known utilities or something like that. So for example, if we do not want to see if certain process has attached to us, we can simply iterate through all the processes and then we can compare them with known analysis tools, and if some such tools are running, we can simply exit the code or probably change behavior. Or if our code is started from inside a debugger, generally the debugger process will be somewhere in parent process chain from our own process. So we can start from own PID, then we can check who is our parent, then who is its own parent, and so on, and somewhere in the chain that debugger process will be there. So and for Linux, the common method to figure out if some other process is attached has attached to our own process as a debugger, the simple method is to read this /proc self/stat file, and the fourth entry is the PID of process which is trying to debug our own process. Or we can try to figure out whichever process is our own parent process, and then we can try to match them with known tools. For example, I am trying to match them here with GDB and LLDB server, that is debugger from LLVM, and then we can simply check for those paths. And this method is really simple to for full implementation actually. So if we go here, okay, here is the code, detect process. This is how we are detecting here. We read this proc self/stat process, and then we try to see which process is attached to our own process. So if we run this, for example, we can go back to this one and we do this. Simply it says that I am not being debugged, and if we do this and run it, it says I am being debugged because it sees that GDB is in its parent process chain. So this is yet another method. Then we can try to figure out if there are certain artifacts which are generally created when a debugger is trying to debug a process. We can probably check for them. So most common method that you can probably find on internet on way too many blogs is called basically attaching to ptrace. So basically you use the ptrace is called to attach to your own process as a debugger. And the thing is that only one process is allowed to attach to a process at any given time, as in no two different processes can attach to same target process at same time. So if this particular call fails, that means that some other process has already attached to our own process. So we can do this very simple check here, but the problem with this is that an analyst can probably hook this ptrace call and change its result. So even though we are being debugged, we will not be able to detect it. So this is where this particular technique fails. Then there is a slightly better method from this, and what we do that instead of doing the ptrace once, we repeat the ptrace bunch of times, and since we know that we are doing it, we can obviously check for expected values. So then at each check we can probably maintain some sort of internal state. For example, here I am maintaining a variable, and then after some modifications, some mutations, I can try to check if my internal state is in expected way. For example, if here I am modifying this variable offset, and for first call I am just setting it to 2, for second call I am multiplying it by 3. So after everything has gone successfully, it should be 2 into 3, as in 6. Otherwise there is something else going on. Now this relies upon the fact that the malware analyst is going to hook ptrace blindly and is going to return the same result. So our first condition will still work because ptrace is hooked, but second condition will fail because here we are expecting this ptrace call to fail, but somehow it is still getting succeeded. So this particular modification will not happen. So this relies upon the fact that an analyst will probably not pay attention to figure out that ptrace is being used at multiple places and some sort of internal state is being maintained. But then there are ways to circumvent this as well, again by tracking how many times ptrace has already been called or from where it is being called, or maybe trying to overwrite that monitor state from somewhere else, something like that. So finally we move to one more technique which relies on invalid system call, but before that we will go through demonstrations of these two. So demo for first one, this code is simply only this much. There is only one ptrace call, there is nothing else going on here. And for second one, it is just a little bit bigger. We are doing the same thing as I demonstrated in the slides, just maintaining a variable and then doing some modifications and checking for expected value. So if we run this ptrace one, it says normal execution, and if I do this inside debugger, it says don't trace me. So basically it is detecting. Similarly, if I run this ptrace true after outside debugger, it runs normally, but if I run it inside debugger, and then again it says don't trace me, because both conditions are not getting satisfied. Only second one is getting satisfied, but not the first one. So this is also working here. And now we move to our next technique, which is relying upon invalid system calls. So here what we are going to do, that instead of using a valid system call, we are going to use an invalid one, as in something that doesn't really exist. So what happens that if we try to execute that, program will simply crash outside debugger. But what we are going to do, that we are going to attach ptrace and wait for that error to happen, then intercept it, then fix this whole thing inside memory and continue execution. So for this example, what I have done, that I have defined this custom syscall which doesn't really exist, and then I have defined a function saying print custom, which simply calls that particular syscall. Now this is where I call that print custom function inside a loop, and here in the loop what I am doing, that I am attaching to myself, and then I am raising a signal to continue. So this basically ensures that the process which is monitoring this part of code gains control whenever something goes wrong here. And then in tracer, what we are going to do, that we are going to monitor this part of code, and we are going to monitor for this particular syscall to trigger, and then we will fix that syscall so it executes correctly. So how we are going to do that? That we are okay. So what we do, that we take the process ID of the process which is running this particular code, and then we wait for that process to change status, and then when the process has changed status and it has stopped, we basically set ptrace options that it will terminate the process on exit. And then what we do, that we configure ptrace again to stop at syscall execution. So what happens here, that whenever a syscall is triggered, as in whenever this particular function is called, this will simply stop and give the control back to us. So what we do, that we copy all the registers and then we check that which syscall is getting called. And here we are checking that if our own custom syscall is getting called, then we do something else, and that something else is basically this. We are putting the correct syscall number and we are setting up its parameters, and then we are overwriting registers for child PID, and then we are asking it to resume execution. So this is a rather convoluted process, yes, and this is not really trivial to implement, but the plus side is that it is also rather difficult to figure out properly, or to analyze it properly if you don't know that something like that is going on. And now we will see the demo for this one. So this is how this whole code looks like, and here what we are doing, that in the beginning we are forking the process, as in this will create a copy of its own process, and then we check that if we are in child process, we run this this part of code. This is the code where we are trying to use our invalid system call. And if we are in parent process, then what we do, that we take the child PID and we run this tracer process where all that ptrace stuff is going on to intercept the syscall, compare to figure out that it is calling our custom syscall, and then we simply are overwriting it with correct syscall number and setting the parameters properly, and then we are simply executing it. So if we run it, it looks something like this. Okay, it says that try attaching debugger to child process. Now here is something to do, and this is something slightly difficult. So for example, if I do this and I run it like this, like we were running first two samples, so we see that okay, nothing happens. It runs exactly as in the previous case, but the thing is that here, instead of attaching to the child process, we attach to parent process. So child process ran completely outside debugger, so nothing really happened. So what we need to do, that we need to ask our debugger to attach to child process instead of parent. So we do this and then we run it again, and now it simply crashes because it is not really going to work. And if we try to see what exactly went wrong, yes, it says something went wrong at ptrace.cpp line 21, and then something failed somewhere deep down inside the libc. So this is the intended behavior for that particular code. If you are trying to debug it, it is going to fail because nothing is going to fix its illegal system call or its parameters. Now then we move to our next artifacts, and that is breakpoint. Breakpoint is something, for example, when you attach to a process, you may want to stop at certain location in code. So breakpoint is a mechanism that debuggers provide, using which you say that okay, whenever the program reaches here, just stop, and I want to see whatever is stored in memory or registers or whatever instructions are going to be executed, something like that. So generally there are two types of breakpoints. One is called software breakpoint, one is called hardware breakpoint. So software breakpoint is generally implemented by overwriting first byte with 0xCC, which is machine code for software interrupt int03. Now we can put a breakpoint by saying by writing full machine code for this instruction, which is 2 bytes, but since there is single byte version available, so generally we go with this one. Most of the debuggers are going to use 0xCC. Then to detect breakpoint, what we can do, that we can to try to see if 0xCC is present at first byte of all the instructions that we want to monitor. So this particular technique works only when that analyst is going to set a breakpoint, otherwise it is not going to work. So generally it is not really used in isolation. It is used in combination with some other techniques that we have already covered. So the most common or we can say the most easy method is to, we can take a pointer where our function is starting, and then we can probably take a list of offsets to instructions. So basically we have the first address, and then we have offsets or indexes where all the instructions are stored, and then we simply loop over them and try to compare their first byte with 0xCC. If 0xCC is found, we can say that it is the breakpoint is set, otherwise we can say that breakpoint is not set. Now as I already told you that there is another variant of this one for same this particular interrupt, and the 2 byte variant is basically 0xCD 0x03. So this is actually for setting up interrupt. For 0xCD is for interrupt part, and 0x03 is for this interrupt number. So whatever interrupt number we are going to use, we can put that particular number after that 0xCD part. This particular case is given special privilege by Intel. So most of the debuggers go with this because at places we may be dealing with single byte instructions, for example 0x90, which is basically an op. So in that case setting up a 2 byte breakpoint is not really a good idea. So 0xCC is what pretty much everyone is using. But in case something is trying to set up 2 byte breakpoint, we can check for first 2 bytes, just like we did for first byte in this previous loop. And for demo part, so there are two ways. For example, if in first case we are checking for breakpoint at only first instruction and not anywhere else, assuming that whoever going to analyze our code is going to stop right at the beginning. So this is most trivial case. Or in a better way, what we are doing here, that we have a list of offsets, and then we figure out where this secret function is located in memory at runtime by typecasting a pointer, and then we pass all this detail to this particular function where we are simply iterating over offsets and comparing the first byte. So if we run this detect breakpoint, it says try breakpoint at secret. So we try to run it under debugger, detect breakpoint 2, and then we simply set a breakpoint somewhere at secret, and then we try to run it, and it says breakpoint detected. So just I so we have covered a bunch of techniques for this anti-debugging things, starting from timing analysis to process check to detecting for various artifacts, and we can extend the same method to detect potential cases for patching. The method will be basically same. We will run this same loop, but instead of checking for this particular byte, we need to either have a duplicate copy of all the code that we want to check, or maybe we can hash the hash the part of code that we want to check at runtime, and then we can compare it with some known good hash, or maybe we can use that hash as a key for some other part of code. So there are other possibilities. If you have any questions, you can probably send me on LinkedIn. This whole presentation deck and all the source code that I demonstrated, or whatever is present in the slides, will also be shared with you by the conference organizers. Thank you.
Thank you so much, sir. Hope you all have learned a lot and had a great experience talking to him. Well, now we are done with all the talks. I would love to thank all the speakers again for taking their times out from the busy schedules for VULNCON 2021. Also, special thanks to the audience who came here to attend the VULNCON and hear the talk. Hope you had a great experience and learned something. So now that we are done with day 1, let's meet tomorrow, same time, same place. Bye bye, take care, sayonara.